So what I want to do next is I want to, at the end of the semester, what I typically do is I just kind of review the different types of equations that we've talked about solving. The first type that we talked about solving way back when, probably on the first day, were separable differential equations. Those are differential equations. Where what you have is you have something of the form dy dx, and that's equal to f of x times g of y. So you can separate variables, get all the x's on one side, all the y's on the other, integrate both sides, and you're good. Okay, so in theory, that's separable differential equations. That's how those all work. After that, we talked about first order linear differential equations. So ODEs, ordinary differential equations. Remember that's what that stands for. And these are differential equations of the form dy dx plus p of xy equals q of x. And it turns out that those are all equations that we can satisfy that we can solve. So the trick is to multiply by your integrating factor mu of x, which was e to the integral of p of x dx, where p was the coefficient of y in our differential equation. So this was our p. And if you multiply both sides by mu, then that turns the left side into the derivative of a product, and then you can integrate both sides, and you're good to go from there. So that's our second type that we did, was first order linear. The next type that we talked about were exact equations. Okay, so exact equations were the equations where you have m dx. So this isn't going to be in differential form, but n dx plus n dy equals 0. And if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x, then we have a solution to our differential equation m dx plus n dy equals 0, n dx plus m dx plus n dy equals 0. We have a solution of the form, capital F of xy equals c, where m is equal to this function differentiated with respect to x, and n is this function differentiated with respect to y. N is that function differentiated with respect to y. So that was exact equations. After that, we talked about substitution. Okay, those problems were very diverse. There were two big types of substitution problems. I'm just going to mention their names, and you can go back and review these as much as you'd like. There were homogeneous ODEs, where a particular substitution of y over x was very useful. And then there were also Bernoulli substitution problems, where, Bernoulli substitution problems are, they basically look like linear ODEs, except you have a y to the n here, and your substitution that you make is you use y to the 1 minus n. So that's your substitution there. Okay. So that's substitution in a nutshell. What we did then is in chapter 3. So this was all chapter 2 stuff. Chapter 1 was really just intro to what we can do with this. We didn't spend a lot of time there. Chapter 3 was all about applications. We did plenty of days of applications of problems. I don't really have too much more to say there. It's just that a lot of the applications that we come up that we can kind of study right away are first order differential equations. So that's why it came right after chapter 2. So chapter 3 is applications. Chapter 4 was about higher order ODEs. So higher order ODEs. So this is things like if we were to have, really, let's just describe the general setup. So let's say I have p sub n of x is a polynomial times the nth derivative of y plus another polynomial p sub n minus 1 of x times the n minus first derivative. And then we're going to do this all the way down to p1 of x times the first derivative plus p0 of x times y. is equal to q of x. Okay, so there's no y's on the right side, just a function of x. And so we studied these in particular cases. These are harder. These are substantially harder than the first order differential equations that we talked about. But we studied these in a few cases. So if q is 0, let's call this, well, it doesn't matter. If q is 0, then that implies that our ODE, this differential equation, is homogeneous. This is a different homogeneity. This is a different notion of homogeneity than we talked about up here. Those are the same word, but they mean different things. So here, a higher order homogeneous differential equation is one where the right side is 0. And we also talked about them, so we started talking about when p sub n of x, when all these polynomials, so all the way down to p1 of x and p0 of x, are constants. And when all these polynomials are constants, we have a nice method, even if it's not homogeneous, we have a nice method of solving those differential equations involving the characteristic function. Solving that, you get your roots, and then knowing whatever we know about the roots and the multiplicities, whether they're real, whether they're real with repeated roots, whether they're complex roots, we know what to do with those. So if the polynomials p sub n minus 1, all of those are constant, then we look for the roots of the characteristic equation and go from there. Okay, so that's what we did there. Now, sometimes it turns out that sometimes not all, if all the polynomials are constants, we have a method for that. There's a few other things that we talked about where everything from here on out is not going to have constant coefficients. Otherwise, we could just do our old methods. So, for example, Cauchy-Euler. This was, again, another chapter 4 topic, but Cauchy-Euler equations are ones where you have ax squared y double prime plus bxy prime plus c times y equals 0. And it turns out that the right thing to do here is to let y be x to the m, and then we can interpret, and again, we know what to do if we have repeated roots. If we have complex roots, we handled all of that. So that's Cauchy-Euler equations. Again, another chapter 4 topic. We also talked about systems of linear differential equations. So systems of linear differential equations. So these are systems where you have something like dx dt is equal to some function of x and y and y prime. All these derivatives are with respect to t. And y prime is equal to some other function g of, say, x, y, and x prime. And then you want to try and figure out, so f is going to be a linear function in x, y, and y prime. And then you want to try and figure out, how do we solve this system, right? How do we find a solution for x and y that satisfies both these equations at the same time? That's what we were after. Okay. After this, in chapter 5, we did applications. So chapter 5 is where we started talking about things like simple harmonic motion and pendulums, where we had the mass in equilibrium, where we had that system, and in forced oscillations. There was a lot of applications that we talked about. I'm not going to recap too much more there, but that application. So this was the mechanical vibrations. That's, again, the differential equations where we had some mass hooked up to a spring, possibly with a dampener. Anyway, so a lot of applications that we talked about there fell in chapter 5, because it turned out that they were higher order differential equations. In chapter 6, we talked about power series. So on the third exam and on the final, you can expect 1, maybe 2 power series. I would say on the final, expect at most 1 maybe 2. I guess it depends on how difficult they are. But we're certainly not going to spend too much more time talking about power series. I think I feel like we've spent enough time. And then finally in chapter 7, this is the one that we've done completely virtually. This is the chapter talking about Laplace transforms and all of the fun that we have therein. Okay, Laplace transforms are pretty cool, but they allow us to solve, again, power series are useful because we can solve differential equations that we couldn't before. At least we can get some sort of an expression. Likewise with Laplace transforms, so we can solve new types of differential equations and some differential equations that we couldn't have solved before, not very easily. Okay, so this is a big overview, big picture overview of our